Hello, everyone, and welcome to the Esri GeoDev webinar series. About 3 years ago, we started this series as a way to continue engaging in developer-related topics and discussions in between Dev Summits. Speaking of which, we have our next Developer Summit coming up in Berlin on November 9th through 12th. We have a lot of new topics, advanced features, and additional functionality to share with you over the next coming months. So be sure to stay connected with us through our GeoDev webinar series page on go.esri.com/geodev or any of our social media accounts at Esri GeoDev. We would love to have conversations like these taking place throughout the year so that when we do meet at one of these Dev Summit conferences, it will be as though we never stopped. We hope you get as much or more out of this webinar than you anticipated. And now we'd like to introduce you to today's webinar, Building Web Apps that Visualize Large Data Sets. Before we get started, I'd like to go over a few items so you know how to participate in today's event. We've taken a screenshot of an example of the attendees interface. You should see something that looks like this on your own computer desktop in the upper right corner. You're listening in using your computer's speaker system by default. If you would prefer to join over the phone, just select Use Telephone in the audio pane and the dial-in information will be displayed. You will also have the opportunity to submit text questions to today's presenter by typing your questions into the Questions pane of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. I would now like to introduce you to our presenter, Christian Akenis. Let's get started, shall we, Christian?
Yeah, thank you, Amy. Go ahead and advance to this slide. Thanks for that introduction, and I'd also like to welcome everyone to this session on building web apps that visualize large data sets. My name is Christian Ekenis. I'm a product engineer on the ArcGIS API for JavaScript. I focus primarily on data visualization, data exploration, how we can build apps that improve in both of those areas, as well as the smart mapping project. I also work on arcade integration with the ArcGIS API for JavaScript. So I do a little bit of everything with the API. And of course, one of my favorite things to do is interact with you, the users, and help improve the API based on your needs. So one of the common questions we get, or that I often hear when working with the ArcGIS API for JavaScript is, how many points can I display in my map? Or sometimes it's more specific, like, can I display 1 million features or 500,000 features in my app? And the answer to that question is going to be different for everybody. It's kind of a complicated question to answer. And not only is it different for each user, so to speak, but it's also different for each project that you might work on. And I'm going to talk about some things that will hopefully build confidence in your ability to answer that question in individual projects. So I want to go ahead and just give you a brief overview so you can know what to expect in this presentation. I'm just going to take a couple minutes initially to talk about initial considerations you should have when building an application that involves a lot of data. And then I'm going to spend the bulk of my presentation on two aspects of this topic. First off, what are we as the JavaScript API and ArcGIS Online, what are we doing to improve performance for you? You may have noticed that over the last few years, we've boosted performance quite a bit, allowing you to render more and more features in your view than ever before. So I'm going to talk about some of the things that we do behind the scenes that allow you to do that. And then on the last section, I want to spend quite a bit of time talking about what you can do to improve performance in your applications, to improve performance. And so that can involve a number of different things such as visualization techniques and also data prep and processing. And when it comes to the visualization techniques, that's really all about improving understanding as well, because ultimately that's the goal. We want to improve understanding for the user. And with that, let's go ahead and dive right in and talk about what you should be asking yourself before you start developing an app. And I know that these questions may seem a bit rudimentary, but let's take a look at them from the lens of large data sets. First off, you need to know your audience. Are you developing an app that's for just a few specialized users? Are they accessing it publicly or privately? Or does it even have a potential to go viral? And those questions tie directly into the next point on devices. Is this app designed only for desktop devices, or do you need to consider mobile and tablets as well? When we talk about the potential to go viral, really apps go viral through mobile devices. You don't see it quite as much in the desktop world. So if you're building a public-facing application and you think that it has potential to go viral, you definitely need to consider the limits that you might have on mobile and tablets. But that being said, if you have just a few specialized users, and I'll show you an application that could apply to a little later, it's probably appropriate to only develop it for desktop if you know that they are accessing it only on desktops. And so another thing you need to consider is what is the appropriate way to visualize this data based on the scale. You might be aware of different ways that people can view the data, but if it's really designed to be viewed at a particular extent or scale, you can appropriately generalize that data or reduce the number of features in using various techniques. So I'm going to go over all of these things in just a minute. Okay, so first off, what is it that the ArcGIS JavaScript API and ArcGIS Online are doing for you behind the scenes to improve the performance of your applications? And the most fundamental way that we have improved performance is through feature tiles. These are dynamic, efficient, flexible, and it's a scalable way to bring data to the client. Now, when we traditionally think of querying features from a feature service, you might think of it in this particular representation. You have a client, which is your browser or the application, that executes a request for features to the feature service. And commonly, you have worked with that by JSON responses. So those features come back, and then you can work with them in your browser. This is a pattern that many of you have likely used within your apps, where maybe a user will click a button, or they'll interact with their map in some way, and then it will execute a query behind the scenes, and then you will be delivered the payload, and then you'll be able to work with your features in a particular way. When we talk about feature tiles, we are requesting, where the client is requesting the data in a tiled format. So when it requests the data from the feature service, it'll come back as dynamic feature tiles. These are repeatable queries that through a series of caching or levels of caches, we can improve performance for not just you, but other people that might be accessing that application. And I'll demonstrate what that looks like in just a second. But first I want to cover this slide, which talks about the various levels of caching that goes on behind the scenes. Whenever you execute a tiled query or a feature tiled query, that query is sent to the feature layer. And of course, if it's cacheable, your browser can cache it, and if that cache exists, you can take advantage of that and leverage it. But where I believe the real power comes in is these levels beyond that. We cache feature tiles on the CDN and also on the service in the feature tile cache. And so when the client executes a query for a feature tile, it'll check to see if that tile exists in any of these places. If it's not cached anywhere, it's going to query the underlying database directly. Of course, that's the least performant and least scalable method of getting features. But if once that query is executed, that will be cached on the service and also on the CDN, so that, say, if I'm executing a query here in Redlands, California, using an application, and someone in Buenos Aires, Argentina, executes the exact same query, that they'll be able to leverage that CDN cache if it's a public-facing app. You also note that for private layers, they do not have the ability to, and because we don't want to expose private data in a public CDN. All right, well, so let's look at an example here. This is a layer showing about 940,000 building footprints in New York City. So we got a lot of features, it's loaded in the browser, and when we query this data, we query it for one tile at a time. And so you can see various sizes here. We'll start at larger tiles, we'll execute a query, and if the size or the number of features exceeds a certain number, we'll subdivide that query appropriately down to a certain number of levels before we're able to get all those features. And so if we open up the network tab, and I'll show this in another app as well, we can look at what we're doing kind of to execute this query, looking at the query string params. So first off, we're executing, or we're requesting this data in PBF format. That stands for Protocol Binary Format. That's an optimized format for data transfer. I also want to call attention to this outfields property here. This layer could have many features. It could have up to 50 attributes or whatever. In this particular case, it could have up to say 50 attributes. So depending on the number of attributes that are available or that are needed for rendering, the JavaScript API will Hello?
We can hear you now.
They can? Okay.
Yeah.
All right. So the number so this layer could have 50 attributes, and if we were to query for all those attributes, it would be a huge detriment to your performance. So it'd take a long time to load all those features. But the JavaScript API is smart about knowing what it should request or what's actually required for rendering. In this particular case, we're only requesting the object ID field and the construction year attribute because that's what's driving the color of these polygons. So we can significantly reduce our payload size by only requesting what we need. Also, the quantization parameters. These parameters ensure that we're requesting no more than one vertex per pixel. So when you have a very detailed data set, such as polygons or lines that may have multiple vertices, when you're zoomed out to a scale like this, you'll likely have pixels that have many overlapping vertices, even within the same feature or overlapping features. This ensures that we're only getting one per pixel. And you can see that in this tolerance parameter here, where that indicates the real world units or the size of the pixel in real world units. So the size of the pixel is 38 meters, and we're gonna only request features based on that tolerance. But the most important thing that this is showing is the result type is tile. That's what the client uses to indicate to the service that this is a repeatable query. We know that users will load this app at this extent multiple times, so all of these tiles that we're querying can be cached. And if we look at the response, you can see that we're requesting this using the HTTP2 protocol, and that it is being that the tiles are delivered using Brotli compression. That's a much more efficient way to compress your data than gzip. And where this xcache flag here indicates that this was returned from the CDN cache that hit from CloudFront. And the Esri xtiles cache indicates that these tiles were also cached on the server. So we didn't actually need to get to that point because they already existed on the CDN. But when it was not there, you see some of those hits below. The last two were a miss from CloudFront that was returned from the server cache. And then this is what the data looks like. This is a JSON representation of what the PBF response might look like. So you might look at these geometries here and think that they look a little weird. And that's because we've optimized that the way we fetch those geometries so it's highly efficient. In this case, you'll note that the first coordinate in the polygon is the screen. It's basically the screen coordinates of the first vertex. And then every other coordinate after that in these rings, these zeros and ones and negative ones, those are the coordinates relative to that originating point. And the JavaScript API knows how to translate those back into real world coordinates using that this translation parameter. We've also made a lot of strides in the last year on improving the processing and preparing of features to be drawn in the graphics card, particularly with lines. So there we go. So when it comes to drawing lines, there's needs to be a balance between overall display quality and performance. You may know that when you render a line, you can use any number of different joins. There's round joins, bevel joins, miter joins, or just a straight quad where there's not really a join at all. Probably the join that looks the best, if you ask most people, is the round join. But that join takes a lot more processing time and therefore requires a lot more memory as well. So when we were working on optimizing this process, we did a lot of testing to see how much it was actually worth it to use the round join at certain line widths. And we determined that when you hit about 2.5 pixels of width or less on lines, you can't really see a visual difference between any of these joins, even with the quads. So we opt to actually render the lines with just those two segments if the line is very thin, which many applications actually do that already. It's, they're either half a pixel or one pixel wide. And so we're not going to even bother attempting a round join at that point because you're not going to tell a difference anyway. So that's just one way that we can improve performance in behalf of you, even when you're specifying a round join. And one, of course, you thicken that line above 2.5 pixels, then you're going to see that nicer round join on your lines, and it will be obvious then. And this animated GIF that you see here is a bit outdated. That shows the difference of loading features in the 4.9 version of the API versus 4.13. But I think it's a good illustration of some of the progress that we've made. If you go back a few years, probably 5 years or so or before, we were barely able to render all 3,000 US counties. And that was a big accomplishment, and it was amazing to render that much data in the browser then. But now we can render much more than that. You saw 900,000 building footprints, but these are more complex geometries than what you saw in those New York buildings. And we can render 30,000 of them, or even more than that. We've been able to render all of the census tracts, which is, I believe, about 70,000 polygons in the United States. But in both versions of the API, you can still load all of that data, but you'll note that in the 4.13 version, which came a year after 4.9, that the features loaded and drew much faster than before. So we're improving the speed, the accuracy, the memory profile, and ultimately we're improving the triangulation, which results in those faster lines that are drawing. And I also wanted to point out that we are continually improving this performance. So if I start to load this layer of New York buildings again, you'll note how fast it loads on our development branch that we're currently working on versus the most updated release of 4.15, which came out in February. So even between these two versions, there's a lot of potential for improving performance. Now, I'm not going to promise that the performance will look like this at 4.16, which is still very much a work in progress, but you can see that we are spending a lot of time on trying to improve the performance of your attributes. Now, that line of 250,000 features with 54 attributes, that's not applying to this particular layer, but we are able to bring down a lot of attributes with a lot of features in a very performant way. All right, so those are some of the things that we on the ArcGIS side have done to help improve performance for your applications. Now I'm going to go over things that you can do to further improve your performance. And this can kind of go in two different directions. On the one hand, you can take layers that you already are able to load in your view, though they might be slow, and further optimize them so it's much faster. Or you can take data sets that are so large, there's no way we could render them on their own as they are, but then you can do your own pre-processing to make it work for you on the browser. And I'm going to show you an example of both of those approaches. First, I'm going to talk about scale-dependent filtering. This is a layer that I will be showing of water distribution pipes in Bangkok, Thailand. So I'm going to switch over to my browser to show you what this table looks like in ArcGIS Online. This is a public feature layer I found, and the thing I want to point out here is this total number of features. It's 550,000 lines. So very large layer, and a very detailed one at that. And it's also got a lot of good attributes. We have pipe size here, the material, and other date attributes and inspection things. So a pretty interesting layer. So if I were to add that to my view, I don't see anything here because there's a scale restraint on it. If I zoom in just one level, you start to see these queries off to the right start executing. And you'll note that this is taking a little bit extra time, more extra time than we would want. So you'll notice that in this this X tiles cache, or this X cache parameter, that this is a miss from CloudFront. That's because these tiles were not originally cached on the CDN. If I were to refresh this page, I would hope that I can see that these tiles were indeed cached since it's a public layer. And I'm going to filter by my query parameter here, and we'll see how my connection does. It's been a little spotty this morning, so hopefully it works out here. So again, zoomed out. So if I zoom in, so you start seeing these hits from CloudFront. If I zoom up, the ones that have already been loaded are returned as hits from CloudFront. So we're getting a little bit faster response because these were cached on the CDN and also within my browser. But you'll also note that this is a lot of features. I wrote a function in the app, which is query feature count, so we can log the number of features we see. So we see all of the features, 550,000. Cool. So to those of you who ask, can I render so many features? Can I render 500,000? Yes, you can do that with this version of the API. However, my counter question to that question always is, why do you want to do that? Or is there some other way you could visualize your data? Because this, what I'm looking at, is basically a pink blob. I don't love the way this looks. I don't know that this makes a whole lot of sense to visualize. So is there something else we can do to only show pipes that make sense at this scale? We saw a pipe size parameter. Maybe we could use that to improve or to just basically filter out the data that we don't need to see, because a lot of these are very small pipes that we don't need to be loading at this scale. So if I switch over to the code for this app, you'll see that I'm loading this layer here. And if I set this definition expression to pipe size greater than or equal, if you're familiar with developing GIS applications, this traditionally what users would do is create copies of their layer, and maybe it's different. They've removed features from layers that are intended to be viewed at smaller scales as they're zoomed out. And then as you zoom in, the layer visibility will turn on and allow you to view those features. You don't have to do that with the JavaScript API. You certainly could, but you're loading that layer 3 times, so why bother? Instead, you can watch the view scale and basically set different thresholds based on a particular attribute. This could be a population attribute. It could be something like a line size, like highway traffic, or in this case, pipe size is what I'm using. So I want to show only the larger pipes as I zoom out. And then if I'm zoomed in beyond this 1 to 16,000 scale, I want to show all of my features. All right, so I will go back to my app and refresh it. Hopefully I saved it. I'm not sure if I did. Let's just make sure. Okay, zoom in, and there you go. So now I'm only looking at pipes that are about a size of 300 or more. I'm not sure what the units are because I don't speak the native language, but if we open up our request parameters, you'll see that in action here on the where clause, pipe size greater than 3,000. And as I zoom in further, we'll see more pipes come in. So now we see a little more detail. And, oh, actually, Probably not quite far enough. There we go. I saw more pipes come in. And there's that pipe size greater than or equal to 150. So now I'm seeing a lot more detail at this scale because it's more appropriate for this particular scale. And as I zoom in even further, you'll see the smallest ones come in. And you may also notice that the line width is actually getting thicker. That's a visualization technique I'm using because the same size of thickness doesn't work across all scales. So what that looks like in code is it's controlled in the render of my layer. So when I load my layer, I'm adding this size visual variable. All this is doing is it's looking at the view scale. This is a simple arcade expression. All it's doing is referencing that scale value. And then I map specific scales to specific line widths. Again, this can also take some trial and error, but in the end, it pays off to have a nice visualization. If I set a line width of 6 points to my lines at that smaller scale and I'm zoomed out to the whole city, then it's going to look even worse than it did before, be a giant blob of thick lines. But so I set that to a 0.5 point in width, and then it progressively gets thicker as I zoom in much closer. And those numbers are going to vary based on how dense your features are and how large your layer is extent-wise. So that's one thing you can do to improve performance, because if we look at the numbers here, if you don't filter your data in that initial view, you're still loading 17.7 megabytes of data. That's a lot for the web. And it loads in about 7 seconds on a desktop with a fast network. Obviously, I'm not on a fast network right now, so it might take a little longer than that. But then experimenting with other types of filters, you see that those number of features are progressively reduced and that the speed is getting a little better. But still, even in this case of only showing a pipe size of 300 or more, I'm still loading 100,000 features in that case. And it still amounts to 11 megs worth of data. So if you're designing an app like this for a mobile device, this data sets, you're probably gonna have to be a lot more aggressive there. Either show much fewer features at this scale, or set a visibility constraint even more aggressively, so as they zoom in, they don't see the features until they come in. So filtering your scale by attributes is just one method you can use to improve at least initial load performance of your app. Now, I want to talk about clustering a little bit here too. This isn't so much about loading performance, but this is more about visual understanding. If you look at this layer here, this is a layer of 103,000 trees or so in Eugene, Oregon. If you look at the legend here off to the right, you can see that these are visualized using color. But I'm just looking at the species name of each of these trees and visualizing it differently by color. Now, it's cool that I can load 103,000 features. I think for a lot of you, that would make you happy to be able to load that many, perhaps even more. But I always go back to that original question that I was asking before is, what do you want to do with 103,000 points? In this particular view, at this extent, they're all tightly compact and they're hard to distinguish. It's hard to see visual patterns that might otherwise be interesting. And so that's why we have clustering. It's a method of what we call feature reduction in the JavaScript API. And instead of showing you in code, I'm actually loading this in the new map viewer beta so I can show you how stark the difference is. If I toggle this switch down here at the bottom to enable clustering, you can now see that those features have been reduced to clusters. And I can even be a little more aggressive on the clustering by bumping that up a little bit so I get fewer clusters. Now I see something interesting. I can see some patterns. I see these yellow features, these sweet gums in this particular area of the University of Oregon. And if I click the feature, I can see that that represents a certain number of trees, in this particular case, 1,100, and that the predominant type is in fact that sweet gum species as indicated by the color. So what I like about our implementation of clustering is that it tells you something about the features in the cluster using the renderer. So the predominant type will be indicated by the symbol of the cluster. In this case, it's just the color. And then the size will show the number of features. Now this by itself does not necessarily improve the performance of your app. This is more about improving understanding, so the users know more about your data. So this is something that really proving a point that you might not want to render 1,000,000 points in your view just all at once, because it's just hard to understand. If you aggregate it in some way, in this case it's a client-side aggregation, then you can improve understanding. And in some cases, you'll need to do aggregation ahead of time in the data processing step. So there you can see the differences between the two. Now I want to spend the rest of the time talking about this topic, data prep and processing. There's various different ways you can look at this. You can restructure your data, generalize your geometries, thin them out, or remove unnecessary attributes. I'm going to demonstrate at least 3 or 4 of these topics using this app, OneOcean. If you tuned into Dev Summit Plenary this year, then you may have already seen this application demo. I'm going to first demonstrate the application and show some of the code that went into creating it. And then I'm going to talk about what went in behind the scenes that I had to do, and as well as others, in order to make this data set work. So here's the application. I've got about 85,000 points or so of ocean points that are, this is a data set called the ecological marine units, and I'm rendering this in the spillhouse projection. The spillhouse projection, it looks a little strange at first, but it's also really cool because it renders the ocean as one body of water. And it's a really neat way to view oceanic data such as this one. So let me just give you a preview of this data before I dive into that app. This is open data that is provided by Esri. You can access it here if you just do a search for ecological marine units. And note that this was that this data set was created with between a collaboration of a bunch of different organizations, including Esri. And it is freely available to you. You can download this data and work with it in your apps. And it contains some interesting attributes, such as the direction the water is moving, the velocity, the temperature, the salinity, dissolved oxygen, nitrates, all sorts of data at your fingertips. When I first saw it, I wanted to get my hands on it and create an app. And in collaboration with my colleague Jeremy and Keith, we were able to create this application. So we're looking at ocean salinity right now, where the darker areas indicate higher salinity and the lighter areas are lower salinity. And note that as I move my cursor around the view, I am querying the salinity values for that particular point at a bunch of different depth levels and rendering those numbers into a scatter chart off to the left. So you can see how salinity varies by ocean depth. Really cool, really fast and responsive. The reason this is so fast is because I'm leveraging the JS API's client-side query engine. It's very fast, very efficient, and allows you to do very interactive applications such as this one. I can switch to another attribute, such as temperature, and the visualization will update very rapidly. And I've also added this depth slider that allows me to change the look, or basically visualize based on different depths. So you'll see how not only the salinity, but the temperature varies as you go deeper into the ocean. And of course it gets colder. And note how fast this is updating. That's because we're leveraging the GPU on the device to render this data. In fact, when we query data to the client, the GPU has access to all those features, allowing you to update the visualization without having to reprocess individual geometries that are rendered on the graphics card. So it's really cool and really powerful. If I switch over to my code, I'm just going to show you one snippet of what happens each time that slider handle moves. Each time it moves, I'm creating essentially a new render on my layer. And that new layer is I'm not changing the color values to sort of fake it. I'm actually changing the underlying data. So if we look at this size visual variable, oh, sorry, let's first look at color. I'll look at color. I'm referencing a particular field in my data. If we look back at that layer, I've got temperature for a point at depth level 1, 2, 3, or 4. those depth levels indicate a slider position. So every time that slider changes, this field reference will change. And every time it changes also, it changes a different, it changes a reference to a different velocity field for the size. So when I turn on the size attribute or visual variable, you'll notice this one coming up. And because one size doesn't fit for all scales, similarly to what you saw with the lines, I'm going to change the sizes of my points so that they grow as I zoom in. And then I will also use a rotation variable to rotate the icon based on the direction of the flow. So let's go back to the app and see what that all looks like. We'll go back up to close to the surface. And when I show currents, what I'm doing, let's see if it updates. There we go. So it updated pretty quickly. And now I can immediately see areas where there are ocean currents based on how fast the water is moving. So points that are moving faster, or points where water is moving faster, are rendered larger than others. So you can see a cool pattern of ocean currents in this projection. And this projection actually preserves direction. So you see the true direction of those currents. If I zoom in, you'll see that these icons will grow so that I can see these patterns more visibly. Again, my internet's a little slow today. There we go. So now I'm looking at the equatorial currents. So now you can see how where there's faster water and slower water, and you can more easily see the direction that the water is moving. Something that I learned while exploring this data set is that the direction actually can change as you go down in depth. So we're actually looking at several different ocean currents here. There's different currents on the surface, and then there's different currents here at about, let's see, 95 meters below the surface. And as I update the slider, I can do it very fast, up to 60 frames per second. So really, really cool stuff you can do. Let's see if I can explore this data a little more. Again, this also goes to show how having a large data set like this might not work, because if you have a slow connection, it really depends on what you can do. So because of my slow connection right now, I can't really do a whole lot with this app. So while it's cool in practice, it's also not practical if you're working on networks that don't that aren't fast. So this is a particularly cool pattern here, the Agulhas current. And if I use this filter tool, basically the user can draw a line here, and it will filter that data within a certain distance. And you can see that it renders on that histogram. I'm going to toggle off the current so it's a little easier to see. And you can update that distance to query, or even the depth, and that histogram and the render update very, very quickly. All right, so that's just a small demonstration of what that app does. And I've only got a few minutes here, so I gotta move quickly through these slides. But basically, this is the data that you have access to on ArcGIS Online. It's an ArcGIS Pro package. And when I first looked at it, I was horrified to see how large it was. It's 4 gigabytes worth of data. So if I wanted to use this in the browser like I'm doing here, I got to do something in addition to it. So first, get to know your data. I learned that this data consists of 52 million points, just enormous. And it's basically, points located at every quarter degree of latitude and longitude, up to 102 different levels of depth, going down to 5,000 meters below at certain parts of the ocean. So in addition to that, we also have 12 attributes per point. So we have a massive, massive data set that's got a fine resolution. So the goal is to get this total download as small as possible. So if you look at this table off to the left, right, this is sort of a small version of what we're looking at on a much, much smaller scale. So each color, there's a pink color and a blue color highlighting those rows. That indicates a row of the similar color indicates the same XY or latitude longitude location, but at different depth levels. So you'll see same XYs, different temperatures, different levels of depth. So the first idea was to flatten this table, basically squish those points so we only represent them with one XY, basically a 1 point per XY, because we're not interested in 3D in this particular app. We want to view it in Spillhouse. And so the way that you can flatten it is with a spatial join or even a table pivot. ArcGIS Pro is a nice table pivot. And just by doing that alone, we were able to reduce those 52 million points all the way down to 677,000 features. So that is much more reasonable, yet still a little too much, but it also introduces a new problem. We have 10 times the number of fields, or sorry, 102 times the number of fields. We have 1,224 fields, and the hosted feature service limits us to only 1,024. So we got to do something else. But because the 677,000 was still too much, we decided to thin these points out because that resolution seemed much too fine. We wanted to make it a little coarser. So the thought was, let's thin them. Let's only display points at every 1/2 degree. So we'll remove everything else. And just by doing that, using the select by our layer by attribute, and you can see that expression there using the coordinates off to the right here in this slide. Just by doing that, we reduced the number of points down to 84,000. We know we can work with that many features, depending on attributes, of course. So so we go ahead and exported that layer. And if you look at this image, this shows the locations of the original points, the 1/4 degree latitude, longitude points. Those are the orange dots. And then the new layer with the coarser resolution are the blue dots. And you may look at that and at this extent and say like, well, why would you actually want that? Well, we're not going to look at the Gulf of Mexico specifically. If we did, we'd want to keep just those points and filter out all the others. But we want to view this data on a global scale, so we don't need to make it that fine. In fact, when we zoom out to the global scale, it still might be a little too fine. This is showing all 84,000 points rendered with a 3-pixel point or icon. So we get really good coverage still with this. And then the next goal was to reduce the number of columns. So I removed 300 fields right away just because I wanted to get this thing published. So we got it down to 960 fields. And but that was still a whole lot to deal with. So I created a hosted feature layer view and selected only the attributes that we deemed interesting to look at for this particular app. So temperature and salinity, and we also wanted to look at direction and velocity. I didn't know what this would look like. I didn't think it would look as cool as it does initially, but you can definitely see the benefit of just selecting the number of attributes that you need. So I went from 960 fields all the way down to about 317 or so. And the reason why the number of fields there matters is because we want to bring all that data down at once. And I'll touch at that point in the next slide. But some of you may ask or say, well, I can't afford to drop some of these attributes. I want to be able to explore all of them. And that's certainly a reasonable concern. Something that we have experimented with, and I was going to show you this app, but in the interest of time, I won't, is using a comma or pipe separated list of values in a single field. So in working on mapping the COVID-19 crisis, we came across this. So if you look at this table on the bottom, this web, C hospital, web, C ICU, web, C ventilator, those are different attributes that indicate the number of hospital beds used, ICU beds, and ventilators that might be required for a hospital to use on a particular day of the pandemic. And so in that first index, that's 0 across the board, but if you go 10 numbers in, that would indicate the numbers on the 10th day of the pandemic. And so instead of using separate fields, you can actually squish all those values into a single column and basically store it as a string of separated values. And then you can use an arcade expression, which is what we did. And this is the capacity analysis configurable app template, in case you're curious. That's what we did here is we set this function on the value expression property of the renderer. And what this does, if you look at that highlighted line, the third one from the bottom there, we're just parsing out the value for a particular day that the user indicates on a slider. So if they're looking at the 20th day, then it'll say, I want this hospitalizations number on the 20th day or the 20th position of that separated list, and then I want to cast that as a number. And then you can render that so it's highly interactive. And this is what I was referring to before, is you want to get that download as small as possible, but you also want to make it highly interactive, like I was showing. And that comes at a cost. Basically, to make it highly interactive, you want to request all of your data up front using the outfields parameter. Setting that to a star gives you everything. So I'm requesting all 300 attributes, and that takes a long time to load initially. And you could even see my app chugging a little bit on this particular demo, unfortunately, because my internet has been slow this morning. It was working great yesterday, but today it was a little slow. So that's something that you got to consider, is it's still loading a whole lot of data. In fact, this app, it's looking at 280 megs of uncompressed data. Compressed, it's delivered in 138, but still, that's a lot of data. Definitely not usable for a mobile device. This would be something more for a specialized desktop user. And so yeah, the initial load time is longer, but the UX pays off, I believe. You get a nice user experience where they can explore in a fast, interactive way. So I will conclude now, so we have time for questions. But in the conclusion, I just want to reiterate the 2 points. If there's any 2 points to take away, one is, yes, we're doing a whole lot behind the scenes to help you out. This data set of 280 megs would not have been possible just a year or two ago. But because of the improvements we're making, we're able to take a data set that is so massive it's not able to be used and do our own processing and still leverage what the JavaScript API and ArcGIS Online are doing for us. But the second point to take away is that doesn't take away your responsibility to do what you can to optimize your apps. Think about what you can do to make it more understandable, but also to remove excess data that you absolutely don't need. And that can be done by reducing the features like I showed in my app, or by aggregating them to something else. It could be points into polygons or some other method. But remember, it's kind of a twofold mission. Is like, you want it to be a fast performing app, but you also want it to be an understandable one. And I think the two concepts play well together. And so before turning it back over to Amy, who will field the questions, I want to point you to some additional resources on these slides. You can access this app on my GitHub account. Also, there's an OneOcean hub, which points you to other resources that show ocean data if you're interested in that. And also, my Dev Summit data and slides are available. I presented this app at the Dev Summit, so you can see those resources as well. And I've also written a number of articles about this topic that you can refer to. With that, I'm going to go ahead and turn it back over to Amy, who will field questions. Amy?
Thank you, Christian. We're now going to begin answering the questions submitted during today's presentation. We've received quite a few, and we will try to get through as many as possible, but whatever we do not get to today, we will address in a GeoNet blog post after this webinar. It will be located under the Geo Developers community on GeoNet. As a reminder, you can still submit questions through the questions pane in your attendee control panel. Our first question, Christian, is there a maximum limit to the number of points in the layer that can be clustered?
Great question. There is in the 3x API, that's 50,000, but on the 4x API, there is no limit other than what your browser can handle. So I talked about how it depends on whether you're using a mobile device or desktop device. However number of features you can render, if you can render 500,000, we can cluster 500,000. If it's, less than that, then, so no, there's no real limit that the JavaScript API caps, but it's really up to your device. So it's your device limit, not an API limit.
Okay, great. Perfect. Thank you. What's the difference between feature tiles and vector tiles?
Also, great question. Difference between feature tiles and vector tiles is they use similar technology. They're both delivered in PBF format, things like that. But the feature tiles are dynamic. And what I mean by that is you can interact with them. They're actual real features. So when a feature tile is delivered to the client, it brings all of those geometries down individually, so you can interact with it the way I showed in the OneOcean app. A vector tile layer, if I published that using OneOcean app, I could get probably a better load time because I am loading just what I want to see visually, but I can't really interact with that layer. I can't hover over it, query it. I can't get charts from it. So it's really the interactivity component of it. So feature tiles, they're dynamic. They're also generated on the fly. So if you make an edit, an old tile will be discarded and then a new one will be created when you request the data. Whereas the vector tile layer, you have to pre-cook your tiles ahead of time. So there's a number of differences there, but just note that feature tiles are for interactivity and vector tiles are not. They're just for display.
All right. To what degree can these large data optimization tips be used with the 3x version of the API?
So there are certain things that we are doing in the 3x API kind of on our side, like delivering the data in PBF format and quantization and feature tiles, like that's all part of the 3x API. Um, I would say it's very, very similar, but we are paying more attention to improving performance on the 4x side. So 3x API, we do render our features with WebGL, but there are more limits in 3x than in 4x. So um, I'm not sure if that answers the question. I would just say that you can, I don't know if I can adequately define to what degree you can do it, but you can certainly, all of the things that you can do to pre-process your data, you can do for 3x and it all applies there. But we are leveraging feature tiles on the 3x side. I do want to iterate that as well as WebGL, but 4x we're paying more attention to at this time.
All right, perfect. Thanks, Christian. Can we use these rendering techniques with graphics layers or only feature layers?
Also a good question. The rendering technique, we have improved the performance of graphic layers, but you're going to get the most bang for your buck using feature layers. And that includes the client-side feature layer. So if I created a feature layer with client-side graphics and I wanted to have these fast visual updates on the layer, like I was showing with that ocean data, you can certainly do that on a client-side feature layer. You're not going to see that so much with the graphics layer because you don't have a renderer there. You only have that on the feature layer and other similar open layers like GeoJSON and CSV. So I would definitely promote the feature layer there.
All right, perfect. Can you show us where the quantization parameter is defined and for which type of services?
The quantization parameter that's something that exists on the core feature service capabilities. So if I went into, let me see if I have a layer here. So let's go to overview and then got to move this control panel. So if I look at my service endpoint and then these are all 900 fields, I have to scroll down. And then here's the query. So you can specify quantization parameters here in this query. That's a feature service or a REST API thing you can use. And query there. And I believe that's also available on the query object in the JavaScript API. But that's something that we're doing for you. You don't need to worry about that. You're not going to set your own quantization parameters. The JavaScript API will handle that for you.
All right, thank you. And for our last question, do you have suggestions for improving rendering of large data sets of 3D scene layers?
3D scene layers, good question. I'm not quite as familiar, to be perfectly honest, but I will tell you that scene layers are already optimized for rendering more features, like building scene layers, point scene layers, and even the integrated mesh scene layers. Just like what our team here in Redlands is doing to improve performance on the 2D side, our 3D team is doing a lot of good work on improving performance on their side. So I don't know that I would have specific recommendations that you should use on scene layers that would be different here, other than only render what you need. But I know that those services are optimized for streaming large amounts of data. So you're going to get much more performance out of a scene layer in 3D than you will out of a feature layer in 3D.
All right. Well, thank you, Christian, and thank you everyone for attending today's webinar, Building Web Apps that Visualize Large Data Sets. We did receive a lot of questions that we didn't get to, but like I said, we will be posting them in GeoNet under the Geo Developers Community space, so you can take a look there. If you have any additional questions, please feel free to contact me using my email address in your follow-up email that you receive. Once you leave today's webinar, you will receive a survey on the presentation, and we would greatly appreciate if you would complete that and provide your feedback. We will be providing a recording of this presentation. It will be available within 7 to 10 business days on the go.esri.com/geodev page. And on behalf of Esri and our presenter, thank you for joining us today and have a great rest of your day.